All right, so we're going to go ahead and get started. So thank you everybody for joining. Today we have Dr. Carlos Michelen. He's a senior member of the technical staff in Sandia National Laboratories Water Power Technologies Office. His research interests include machine learning and data science methods for marine renewable energy applications, open source code development, statistical methods, computational fluid mechanics, and computational modeling of wave energy converters. He's worked on the development of several Sandia wave energy converter tools, including WECSIM and WECOP tool. He received his bachelor's and master's in naval architecture and marine energy from the University of Michigan, with minors in oceanography and international engineering. And Carlos obtained his PhD from Virginia Tech, where his dissertation focused on machine learning and data assimilation for turbulence monitoring. So please join me in welcoming Carlos.
All right. Hi, everyone. I'll speak about control co-design of wave energy converters. So just a brief outline of the talk. I'll start with an introduction to marine energy and Sandia. I'll then talk about control co-design, and then go into a little bit more detail about WEC impedance models and why control co-design worked for WECs. And then about the hydrodynamic model and some interesting work we're doing moving forward. So Sandia National Labs started as part of the Manhattan Project, and it's still mostly a nuclear research lab. It's federally funded research and development center, which means it's owned by the federal government and it does research for the federal government, but it's managed by a private company. And that changes about every 10 years. Right now we're managed by Honeywell. We do everything and anything that's related to national security, including these 5 main portfolios. And I work on the energy and homeland security portfolio at Sandia. So what type of renewable energies do we look at Sandia? These are the ones. I work in marine energy. I've also done some work in offshore wind. But some of my colleagues do geothermal, bioenergy, hydropower, and solar, including both photovoltaic solar, like solar panels, but also concentrated solar. If you've ever seen, we have a big tower with like a bunch of mirrors that concentrate sunlight, and then melt salt and drive a steam turbine. So you might ask, if solar and wind have taken off, why should we focus on marine energy? Why do we need another renewable source? And there's a few reasons. Some advantages of marine energy. Wave energy in specific is highly predictable, at least in the statistical sense, maybe not in the hour-by-hour sense. But you can know what to expect any given month, any given year, energy-wise. And that's very powerful for utilities that have to balance demands and loads. It's very close to residential areas. About 50% of the US lives within 50 miles of the coast. And it's complementary to other renewables. And what do I mean by that? If you think of wind and solar in the northern hemisphere, they tend to lull during the winter. There's less wind and solar energy during the winter. And wave energy is the opposite. It tends to peak during the winter. So if you think of your whole renewable portfolio, let's say if you want to have a 100% renewable energy, if you went with only wind and solar, you would have to install a huge capacity in order to be able to provide 100% during the winter months. But if you do a more distributed portfolio, you can get away with less overall capacity because some of them are more efficient in some seasons than others. And it's the same idea behind diversifying, let's say, your financial portfolio. So how much energy is in the ocean? There's a lot. In the US, in the lower 48, we have about 830 terawatt hours per year of power that we could actually extract. And that's equivalent to about 78 million homes, or 20% of our electricity. This goes up significantly if we include Alaska. Alaska Including Alaska and Hawaii, we go up to 2,300 terawatts hour per year, or more than half of the U.S. Electric demand. There's different types of marine energy. At Sandia, we look at all of this. I personally work mostly on wave energy. But there's wave energy, tidal energy, ocean currents, and river. Now, tidal, ocean current, and river current are all similar, and they're similar to wind in that you have a fluid moving in one direction, and you're extracting energy out of that. Wave energy is fundamentally different from any of those other marine sources and from any other renewable in that it's an oscillating resource. If you think about it, it goes from moving up to moving down, right? Positive to negative, back and forth, several times per minute. So it makes a very unique resource with very unique dynamics and very specific consequences to the way you think about it and you design them. So if you want to learn more about marine energy, I recommend this website. It's a DOE-funded website. And I will show you some slides from here. So if you go to basics, you can learn the basics of marine energy. And here's some examples of wave energy devices. So there's many different archetypes. Unlike wind, it hasn't converged to a single device yet. But normally you extract energy from relative motions. So in this example, the relative motion between those two bodies are hinged. In the point absorber example here, you're extracting energy from the relative motion of the buoy and the ocean floor. And you can imagine a generator inside there being driven by that tether. An oscillating water column, you have the column of water going up and down a duct, driving flow of air up and down. So you can put a bidirectional air turbine in there and extract power that way. There's overtopping devices. So that's, in an overtopping device, when the wave is high, you capture it in a reservoir, and then you use a low head, like hydroelectric generator, like the ones they use in dams. And oscillating surge converter is like a flap hinged to the bottom. It's obviously for relatively shallow water, but you can see the wide diversity of devices that are out there for extracting power from the ocean waves. Right. So I just told you all about why it's a good idea. What are some of the challenges with marine energy? One is difficult engineering. There's very heavy loads in harsh marine environments. So think of biofouling, rust. And also, the thing that makes it attractive is how powerful the ocean is, how concentrated the power is, but that's also what makes it. So you have to sometimes over-design and over-engineer your devices to survive that environment. This all results in high capital installation and operation and maintenance costs. There's also a lot of ocean user conflicts. The ocean surface is used for a lot of things, from fisheries to military zones, protected areas, shipping lanes, and recreation. And then in the US, we have a very complex and costly permitting process. You cannot just go and throw a device in the ocean. There's a lot of bureaucracy involved there. So what do we do at Sandia with marine energy? These are some of the topics, including materials and coatings, code development for modeling. I do a lot of that work, as well as dynamics and controls. Experimental testing, environmental analysis, research characterization. So we do a little bit of everything. And yeah, there's a list of some, if you want to learn more about the topics, there's a list of some good national conferences. And we do hire interns in the summer. It's a big part of the work we do. So if you're interested. All right, so that's a brief introduction to just wave energy and what we do at Sandia. Now I'll give the basics of control code design. So let's first start with the different components of the dynamics of a WEC. The first one is the resource itself, the wave environment. And the wave interacts with your body, with the whole geometry. And that wave structure interactions drives the mechanical power of your device just moving in space. That is then converted into mechanical power, rotational power in your shaft and your power takeoff system. So you have a drivetrain, you have a gear ratio, and then all that is connected eventually to a generator. And then you have the dynamics of the generator itself. So when we're modeling this for designing a control system or for optimizing it, we have to model all of those dynamics, all of those interactions. Sometimes we refer to that as like wave to wire. And pictured here is Aqua Harmonics. They're a company in the West Coast that are developing a device. And I put the picture here. There's many companies, but I like the way they've done their visualization. So if you go to the website, you can see like the different components, like the generator, the hull itself, mooring lines. So it's pretty cool visualization that shows you just everything that goes into the dynamics of a wave energy converter. So control co-design, the way I like to think about it is if you're optimizing, let's say the way we normally did it, we will start with, let's just design a WEC. Let's design the geometry, right? Decide how big it is, what shape it has, how is it moved to the floor. And we do some optimization, maybe not very thorough, but we try to optimize it so that we get the most energy transferred from the wave into the mechanical motion of the hull. So let's say we're talking heave, the up and down motion of your boom. And we might come up with this design, if that horizontal line represents like the space of all possible designs. And then after we have a design, we start looking at the controllers. Well, now that we have a WEC, how can we control it so we extract the most power possible? And we might do an optimization along that line and come up with this design. But it's likely suboptimal, and the reason being that this whole space ended up being unexplored. And if you consider both the physical design of the device and your controller simultaneously, the optimal answer you might get might be somewhere in this red area. So that's a high level kind of the idea of control co-design. Obviously you have way more parameters. Just the design itself wouldn't be a single parameter. You have different geometric parameters, different parameters in the generator and your power takeoff system. So this is kind of a history of how we've thought about the design process, at least in our group at Sandia. And if you're an electrical engineer or a control engineer, most of this will be obvious. But for us who came from hydrodynamics and started looking at WEC designs for the first time, the program was founded in 2012. None of this was obvious to us at the beginning. So we start from like, how do we design the geometry, the hull itself, and then we apply the controllers. But then we learned that you can't just do that. You have to actually model the dynamics and losses within the power takeoff itself. So initially, for the power takeoff, we'll just do a simple damping term and model our power extraction like that. But we soon found out, well, that won't cut it. We need to actually model the generator dynamics and all the dynamics of the entire power takeoff chain. But then we were still optimizing the controller at the end. So dark blue is what we're optimizing. And lighter blue is what we're designing one off. What we started doing recently is co-design, where we don't just optimize the controller, but we optimize the controller and the physical device, whether that's just the power takeoff or both the power takeoff and the geometry, all together, all simultaneously. So yeah, it goes from like bad, what we're doing 10 years ago, to better, what we're doing 5 years ago, and then what we've been doing the last like 3 years or so. And again, if we had started from a different field, like electrical controls, this might have been obvious from the beginning. Yes?
Okay, so what are we controlling? Like, you have a circuit, right? It's like, the body is moving and then you get...
So in this simple example, so you can control many different things. In the example that we use to illustrate this, which is a single buoy, what you're controlling is the torque in your generator. So the torque in the generator has several effects. If you resist motion by applying torque, you produce energy, which is what you want. But that torque also translates to a force on the buoy, so you affect the dynamics. So there's an tuning there, an optional way to control that, so you end up extracting the most energy possible.
So it's like if you manipulate the torque in the wrong way, then the buoy won't move.
Yeah, if you put too much torque to try to extract the most energy, it won't move at all.
Yeah.
And if you put too little torque, then you're not extracting enough. And like you'll see, like, it's not just a single magnitude, it's the dynamics of it too. It's when and how much, and continuously changing it, so it complements the dynamics of the web and the waves and so on. So the way we do control co-design in our group is with the pseudo-spectral method. So if we have an ODE that describes our system, the dynamics of our system, I'm sure most of you have seen like initial value problems where, like Newton's method or Brunsch-Kutta, where you start with an initial value and then you take a very small time step and figure out the next position and next velocity. And that's what's illustrated on red. The pseudo-spectral method, what it does is it's an optimization, a gradient-based optimization of whatever you're trying to optimize, like power extraction. And then the ODEs, your dynamics, are enforced as a constraint to that optimization. So you start with some random initial guess, but your optimizer will converge to the optimal design that satisfies those constraints. So this is kind of illustrated with the blue here. If you look at the whole time series at once. Even though it has spectral in the name, it is a time domain solver, which means it's fully nonlinear. The pseudo-spectral comes from the fact that the time series, we just represent them as Fourier coefficients. And that's what we use as our state. So this is what the pseudo-spectral problem looks like. We're minimizing some function J that could be extract the most electrical energy possible. Such that the dynamics are respected. So this R of x equals 0, it's our dynamic equations, the ODEs that govern the system in residual form. And then we can add arbitrary constraints. And some of the constraints we use, the most common one we use is the maximum torque that the generator can provide. And that's bidirectional, so there's a maximum and a minimum. For example, 600 Newton meters and negative 600 Newton meters. And the states that the optimizer is solving includes both the dynamic states, so the position of the device or the velocity of the device, and the controller. So here's where you can see that the dynamic state is part of the optimizer. And then it has to make sure that it obeys your dynamic equations instead of solving the dynamic equations explicitly. And in this framework, we find the optimal trajectory of the controller and the device dynamics that result in the most power output. And what we end up doing is having two optimization loops. So the inner optimization loop finds the optimal controller for a given design, and then the outer optimization loop goes through your design parameters. So let's say you're changing the gear ratio in your power transmission, or you're changing the radius of your buoy. That's the outer loop optimization. And then for every possible design that your optimization algorithm considers, we run the inner optimization that does the optimal controller for that design. I was talking about the residual Rx. So your dynamics are normally expressed using Newton's second law as mass times acceleration equals sum of forces. So your inertial properties plus all the forces acting on your device. In the simplest case, the forces acting on your device are the hydrodynamic forces, so the wave-structure interaction, and then the force from your power takeoff, so the generator back-propagated to your conversion chain. So what does this look like? If you model it as a simple mass spring damper, your ODE looks like this below. It's very simple: mass times acceleration, a damping term times velocity, and a spring term. equals the external forces. And then this is a diagram of how we would model a simple WEC. You have the buoy, you have a gear ratio here that converts from linear motion to rotational motion, some inertia in your shaft, and then the generator model. So how do we do the optimization? The inner optimization is for the optimal controller. We use automatic differentiation and a gradient base, so you've all seen like going downhill to find the optimal. Automatic differentiation is a rather newer technique, but it's one of the techniques that have allowed machine learning and AI to really explode in the last like 5 years. And the idea is that when you code something on your computer, let's say in MATLAB or Python, the program on the back end will create a computational graph that then it translates to computer language. In automatic differentiation, it creates additionally a gradient graph. And you can do that because at the lower level, there's a finite set of functions in the computer, and we know all the derivatives of those functions. And the benefit is that you can, for the cost of running your function twice, roughly, you can get the gradients in addition to the results of your function. Whereas if you did finite difference, you have to evaluate your function at least once for every input you have. So if you have a big space of parameter, you might have to be running your model many, many times just to get the gradients. So it's a huge improvement over finite difference. It's very fast and lets you do gradient-based optimization for scientific code that normally you have had to rely on finite difference. So as a case study, we have this device called the WaveBot that we've used to study control design at Sandia. There's a picture of the buoy itself, and this shaft up here goes up and connects to our old power takeoff, generator, springs, gear ratios, and all that. And we tested this at the Carter Rock Mask Basin in DC. It's the largest wave tank in the US. And the reason we went to the largest one is when we did hydrodynamic tests, it doesn't matter if you go really small, as long as you're not in the millimeter scale where surface tension matters. There's very accurate scaling laws for scaling the forces and wave structure interactions to real size. That's not the case with power takeoff and generators and that whole chain. Actually, we don't have good scaling laws, and friction has a huge effect the smaller you go, where it has a smaller effect in bigger devices. So when trying to study power takeoff, electricity generation, there's no substitute to going as large as you can. Kapil?
Yeah, I was wondering, how do you make like waves there? What kind of waves can you make in a wave tank? Like,
so this has, I think, almost 200 wave paddles around like 2 sides of the wave tank. So you can create directional waves, you can create irregular waves, all kinds of wave environments. It's one of the biggest tanks in the world. It's the biggest in the US. But it's quite sophisticated, yeah.
Thank you.
So for this device, we try to get the annual average power, so we use a buoy from NOAA. Yes?
I think the last slide, you said the scaling laws don't work well here because power takeoff or something. I didn't quite, do you mean for like all wave energy harvesters? Is this a particular kind that doesn't work for? Or?
No, in general, there's no good scaling laws for like your generator and power takeoff and how it affects your dynamics to go from like model testing to real life scale. Whereas for fluid dynamics, there's Reynolds scaling, there's Froude scaling. For wave energy converters, Froude scaling works really well. So as long as you choose the right wave, so if your device is like 1/20th scale and you want to model a wave of 20-second period, you can calculate what period you need to run in the wave tank to be able to scale the forces.
But this device in particular?
No, for all devices.
Okay.
Yeah.
Got it.
Yeah, scaling up the PTO and the generator and the friction losses, it's not something I think anyone has been able to figure out.
Oh, okay.
Yeah. So what we try to optimize in this case is the annual average power. So we took a buoy from NOAA, they make the data available. This particular buoy is off the shore of Oregon, and it has about 20 years of data every hour, recording the sea state conditions. And what we did is we grouped it into different groups of sea state conditions and modeled how the device performed in each of those, and then weighted based on how often that sea state occurs. And that's how we obtain average annual power. So here are the results. The as-built device has no drivetrain stiffness, so there's no additional spring on the drivetrain itself. And the inertia is about 2 kilograms meter squared. We did optimization, a co-design optimization for drivetrain stiffness and for drivetrain inertia. And again, remember it's a 2-loop system. So the other loop was brute force. We just consider these boxes, each of those boxes. But for each of those boxes, there's an inner loop optimization that uses gradient descent and finds the optimal controller. So you're optimizing at the same time both the controller and the build device. So it's kind of like giving each of those possible designs the best performance you could possibly have to be able to compare them one to the other. And you can see there's quite an improvement to the optimal in this range that we studied in the average electrical power in watts. You might be asking though, what the heck is a negative spring? So if you think of a spring, if you stretch it, it pulls you back, right? And if you push it, it pushes you out. So it opposes the direction of your motion. A negative spring does the opposite. If you move in this direction, it pushes you even more in that direction. But isn't that unstable? The answer is it would be, except for the fact that the whole system already has a very, very high positive stiffness. So if you think about the hydrodynamic stiffness, if you pull the device up, gravity pulls it down. If you push it down, buoyancy pushes it up. So by putting a negative spring on the drivetrain, we're just reducing the effective overall spring stiffness. So I'll pause there. That's the power of co-design. It's being able to evaluate the geometry, not just on how much mechanical power is transferred from the wave to the device, but on how much electrical power you can potentially extract, best case scenario with the optimal controller. Yes?
What type of controller designs like are resulted from optimization, like PEPI?
So when we're doing this type of optimization for guiding the physical design, we use the optimal controller. So it's a completely arbitrary time series. It can do whatever it wants. But then if we're gonna go and deploy this, we either fit a single PI controller to the whole thing, or we do separate PIs based on the wave conditions. So you can switch between controllers. And that ends up being a better approximation of the optimal, but obviously not really as good as the optimal. So I'll talk a little bit about the web impedance model, because it's a bit heavy on the math, but if you follow through, it'll explain why the control co-design works so well for wave energy converters. So let's start with resonance. Resonance is often something engineers try to avoid. So you can think of the Tacoma Narrows Bridge that collapsed just a few months after it was built. This is a pretty funny video. A guy whose bicycle basically exploded because the wheels started resonating. But not always. Sometimes we do take advantage of resonance, including in telecommunications. So there are applications where resonance is desired. They're rare in engineering, but they exist. Now, what makes something resonate? If you think of pushing someone on a swing, there's two key aspects to making that work. One is the frequency. You have to push, so your forcing has to be approximately the same frequency at which the system is oscillating. So you have to push at the right frequency. If you start pushing twice the frequency, nothing's going to happen. And the second is the phasing. Even if you have the right frequency, you have to push at the right time, right? So the force, the maximum force, and the position and velocity have to align correctly for it to be effective in creating resonance. So for a simple system like a mass spring damper, the frequency of resonance is the natural frequency, which is the square root of your spring stiffness over your mass. So your stiffness and your inertia. If we look at a Bode plot diagram, the different lines have different amount of damping. With no damping, your response is basically infinite at your resonance frequency. And you can see that the phase is also 0 at your resonance frequency. So your forcing and your state, your reaction, your movement, your velocity have to be in phase for there to be resonance. So let's talk a little bit about the concept of an impedance. So we define an impedance C here as the matrix that you multiply your velocity by to get the force. So it's the matrix that relates your force and your velocity. So your state and your external forcing. So it's effort over flow. So if we're thinking of a mechanical system, it's how does a structure respond to a force? It could be the swing. If I push the swing, how does it respond to me pushing it? So the units will be Newton over meters per second, because the effort is a force in Newton, the flow is a velocity in meters per second. If we think of electrical impedance, it'd be voltage over current, ampere. If we think of hydraulic pressure, it'd be the hydraulic pressure in pascals over the volumetric flow. So in general, it measures how much flow you get with some effort put into it. So for a spring mass damper, we can derive the impedance. Easily we start with the ODE that describes the spring mass damper. We describe the position in terms of a phasor, so it'd be a complex amplitude times e to the I omega t. And by replacing that into the ODE, we can get this equation for the impedance, which has a real and an imaginary part, and depends on your damping, your mass, and your stiffness. And again, it relates the external force to your velocity. Now, looking at impedance, we achieve resonance when the phase of the force and the velocity is 0, so when the phase of your impedance is 0, which also means that the imaginary part of the impedance is 0. And the imaginary part of the impedance is your inertia minus your stiffness. Now we can think, why have I talked so much about spring mass dampers? It's because we can think of the WEC problem as a spring mass damper. And this middle box shows how we originally thought about it, just the hydrodynamic effects. So the hydrodynamic effects are the mass of the object, the inertia of the object, but then the added mass. If you stick in fluid, that's a fluid effect. When you move an object in water, it has some virtual mass. So it's a force that scales with velocity. So you can think of it as a virtual inertia. Then you have the hydrostatic stiffness. That's the one I talked about, like buoyancy and gravity. And then you have damping. Comes mostly from creating waves, from radiating waves. It's a loss of energy. And that's how we used to think of WECs and try to optimize it in that framework. What we've started to do now is consider two different spring mass damper systems connected in parallel, with this being your power takeoff device. And this provides a very powerful, practical, and realistic framework for WEC design. So the intrinsic impedance of the device is the hydrodynamic impedance. And it includes your mass and added mass, your radiation damping, and your stiffness. So you have an excitation force, you have your intrinsic impedance, you can relate how the buoy moves if there's no PTO on it. And then we add the PTO forces. So one way to represent this whole system is using electrical circuit diagrams. And then we can borrow a lot of the theory from telecommunications, and it happens to be surprisingly applicable. Again, if you come from the mindset of wind energy and fluid dynamics, you would have never thought of this. But there are systems out there that work with states that are completely oscillating many times. So if you think of electrical power, it might be 60 hertz. That's 60 times per second. That's oscillating positive, negative, positive, negative. And when you consider like a radio tower receiving a signal, and some of it getting reflected and some of it getting absorbed, it's almost a one-to-one analogy with WEX. So this really marked a shift in how we think about modeling wave energy converters and optimizing them. So from one end, you have the excitation force from the wave. Then you have your body that can move in space. Then you have your electrical machine. And finally, you connect that to your output load. And we call this a two-port impedance problem because we're not just looking at the input excitation, we're also looking at the output load and electric machine and what effect it has on the design and dynamics. Not very important right now, but we could simplify this to a single equivalent system. So we can represent this with a single voltage and a single impedance, and that's called the Thevenin equivalence. So the two-port impedance, and sorry for all the math, but the two-port impedance really allows us to think about how to optimize the work. What it's saying is that our PTO design, our power takeoff, should look at both the excitation force and the load. And we can derive two different conditions that we have to match simultaneously. The input impedance of our PTO has to match the intrinsic impedance, as the hydrodynamic impedance of the device in wave excitation. And then the output impedance of the PTO has to match the load impedance. And the good news is that we control the load, that's our controller. So usually we control this load impedance, but we have to choose it so it matches the PTO's output impedance. And this is how we model the PTO. So here you have your efforts, your force, and your voltage. Here you have your flow variables, your current and your velocity. And this matrix here, each of this is really frequency dependent, so it's more than a matrix. But this matrix here relates your flow and effort variables. So what does this mean in practice? In practice, our output impedance, which is defined over there, C out, and all those C22, C11 come from this matrix and depend on your parameters for your power takeoff, so the generator coefficients and gear ratios and so on. So you want to choose your controller to match the output impedance of your PTO, and then you want the input impedance of your PTO to match your intrinsic impedance of the device. And that gives you a framework to think about how to do that. So how can you make the device geometry and how it interacts with waves match the dynamics of your power takeoff system? And this tells you exactly how to do that in the linear model theory to get the most power output. So if you do both of those, you have a controller that matches the output impedance, and you design your power takeoff to work together with your device geometry and dynamics. That's when you really can extract power. So, fortunately, I didn't put it in those pictures, but we have some really cool diagrams that show like all the power available from the ocean, how much gets transferred to your device motions, and then how much gets transferred to your power takeoff. And for many years, we were struggling with like, it's a very inefficient generator, it's a very inefficient power takeoff system, when it wasn't. The inefficient part was transferring from mechanical power to power in the PTO system because of the mismatch in the impedances. So most of the losses are just being reflected, the energy is not absorbed into the power takeoff. Once it was there, once from mechanical energy in the shaft to electrical, it was actually very efficient. So we were focusing on the wrong thing there. It's all about matching all the impedances across that whole wave input to electrical power output. And I'll end with some work we're doing right now. So I gave you an idea of how the hydrodynamic model works, but the theory there's a lot there. But the impedance for the wave structure interaction, the one we call intrinsic impedance, depends on your mass, your added mass, and your radiation damping. And the way we get that added mass and radiation damping, which are fluid effects, is by running a linear potential flow solver for your device. If you're taking fluids, this might make sense. If not, don't worry about it. But basically, we have to discretize the geometry and solve it numerically. What this means in practice is, and we treat it as a preprocessor. We run all the simulations, we get the coefficients we need for the linear model, and then we can run our linear model. But when we're optimizing geometry, we can't do gradient-based optimization because in general the tools that exist out there for solving this fluid problem are not differentiable. Again, the automatic differentiability is a rather new technique and still mostly popular in machine learning. So what we're working right now, actually Capil is leading that work, is on developing our own differentiable BEM solver, so our own differentiable fluid dynamic solver. And we start from scratch. We use the Julia programming language, which is a pretty new and powerful scientific programming language. I like to think of it as like the best of MATLAB combined with the best of Python. It's developed for scientists and mathematicians like MATLAB is, so it's intuitive, but it's open source and free and developed by the general public, not by private companies. And Capil's work is very promising so far. I mean, he's able to match with analytical results for these coefficients, and then he's able to match the gradients that he obtains from automatic differentiation with those from finite difference. Again, finite difference is much more expensive. And finally, I have one slide on system identification. So I talked a lot about the linear model, and I just talked about how we do that computationally, right, with a numerical linear model. But we can do that from experiments too. So we can run experiments to try and come up with the linear coefficients based on a real-life case. And this is also a place where over the last 10 years we've learned a lot. All these coefficients are frequency dependent. So for every frequency you have a different value of added mass and you have a different value of radiation damping. So what we used to do is go and run a bunch of regular waves. You run a wave at one frequency, stop the experiment, then run a new experiment at a different frequency, and different amplitudes. So you end up with hundreds of different test cases. Again, by looking at what's done in other fields that deal with oscillating systems like telecommunications, and applying what they use there to our hydrodynamic cases, we came up with a way of just doing 2 experiments and getting all the data we need to do the system identification. So one is a forced oscillation test, where you have no waves, but you move your device using a random signal. And we use white noise for that. And that's white noise on the generator torque. And then the second test is a diffraction test, and there we do no force on the generator and pink noise on the waves. And the reason we don't use white noise on the waves is that if you give it too broad-banded signal to the wave maker, waves break after a certain stiffness. So pink noise happens to work pretty well. And with just those 2 experiments, we can do the full linear system ID for our device. And all of this I talked today, the negative spring, we have a magnetic spring developed from partners at Portland State University. that we can actually adjust from positive to negative any value we want in some range. This way of doing system ID, we also tested. So we were in Colorado for about 2 months, and we tested all this theory that we had about control code design, about how to do system ID. And the report's available online, and we learned a lot. I think what we're trying to do right now is get that out of the national labs and into the hands of like developers and try to change how the field thinks about the web design problem. And yeah, that's all I have for you. Thank you.
So if anyone has questions?
Are there any private companies that are doing this cover?
So the field of companies right now is like very small startups with like 3 or 5 people, and they're doing everything from financials to asking for grants. So not many, but we have worked with 2 companies that have embraced this way of thinking about it, and they've seen a lot of progress. So CallWave out of Berkeley, they learned to use our code, the WebCup tool, and they took off. They actually optimized it, came up with a new design, and decided to 3D print it and test it. And it did produce more power. So we were impressed with the fact that they were able to pick it up and do more than we could have done ourselves at Sandia. So they're probably the most far advanced in using this. But there's still a lot, like you still see tests going right now that people are like spending a whole month doing frequency by frequency, because you have to wait like 5 minutes between tests for the weather to calm. So there's still some changes to be done in spreading out this information.
2 questions.
Yeah.
First one, have you ever thought about incorporating higher derivatives so that your model could become a little bit more accurate? And the second question is, you kind of lost me at the power takeoff section and why incorporated that. Can you explain what this power takeoff is?
Yes, so linear theory has its limits. It's definitely very approximate, but it's very powerful in that it can give us an analytical framework to think about the problem, and can tell us what in that theory the optimal is. That's something we don't get from more complex models. But we do, at the other opposite end, you have CFD, and we do work there. But then there's an unexplored section of nonlinear models that remains underexplored. And actually, we've started thinking about like how can we do machine learning and discovery and model discovery to come up with better ways of modeling it that are nonlinear but are not as expensive as CFD. And then your second question, so the power takeoff is, imagine the buoy moving up and down. You then have to convert that linear motion into rotational motion of a shaft. That shaft might have a spring, might have a gear ratio, and then that's connected to a generator that has its own internal dynamics and losses, electrical losses.
Oh, so you're just incorporating that as normal. Okay.
You're incorporating those dynamics. So the dynamics of the buoy don't only depend on the excitation force from the wave, it depends on the response from the power takeoff. And those 2 dynamics are roughly on the same time scales, so they're very highly coupled. And you really can't consider them uncoupled like we used to do. If you optimize just considering one end, you end up with suboptimal devices.
Thank you.
Thank you for the presentation. I have one question. I can see it's about optimization, but it's about the environment is given. But the thing is that the environment is changing over time. So is it design adapted to that changing environment? I don't know anything about where you place this.
Yeah, so what we do is we take all the data available for a given site. So in this case, we had 20 years of data, every hour, what the sea state looked like. And then we bin it into smaller spaces. And we do a simulation for each of the bins, and then scale the power output based on how frequent that condition is. Obviously, you could do it, like you could simulate every single hour for the last 20 years, but that would be very expensive and unnecessary. But yeah, we do consider, because the resource is highly seasonal, so you have to consider whole years at a time. You consider 1 year, 2 years, you shouldn't consider like 1.5 years, because it's seasonal, yearly. Like in the winter, there's more energy. In summer, there will be fewer.
Can you explain again why the negative spring coefficient at the high inertial point was generate more power, and then also are there non-magnetic ways to make a negative spring? It's unfamiliar to me.
I've seen like hydraulic negative springs, but I don't know much about them. The one we used was the magnetic one. We collaborated with a professor, Jonathan Bird, at Portland State. He does all kinds of magnetic stuff. He does like a contactless magnetic gear ratio that can go across a wall, for example. So he does pretty cool stuff, but we use one of his magnetic springs. So this is an example. This lighter red line is no spring at all. And then as you go down, it's higher negative springs, so 0, -50, and 100. And we want this input impedance to match our intrinsic impedance. And you can see we match it better over a longer period, but it makes a bigger effect actually on the phase. So we want the imaginary part of the impedance to match this imaginary part of the intrinsic impedance. And you can see with the -100, we match it pretty well in this whole range. Whereas with 0 spring, we only match it pretty well at 1 point. So that's... And we can show that in the equations too. I don't have it here, but we can show how the equations shift your phase and your magnitude, and you want to... And these are the two matching conditions you want.
Is this one wave theory?
No, these are different frequencies.
Okay. Over what? We're just trying to actually visualize what's going on in an actual wave. Like this would be one wave, or that a wave occurs over, like you could have different frequencies of waves, but it's still one wave, right?
Yeah, so it's an irregular wave. It wouldn't be a sinusoidal.
Okay.
So it'd be a irregular signal. But the component of the energy that's in each frequency, if you do a Fourier decomposition, you'd look at how well matched it is with the design.
Okay.
So for the components, for the frequency components of that input wave that are like in this region, if the wave has a lot of power in that region, we'll be performing pretty well there.
Okay, I see. Thank you.
Yeah.
Yeah, so to follow up to that, so so here you haven't highlighted the probability of the frequency occurrence.
I haven't,
Okay.
yes. So this will perform really well for a wave, irregular wave that has a lot of components in that frequency range. There's a question back there?
My original question was about the string technology. So is it something that fixed stiffness for every string? So isn't there any possibility to change the stiffness over time?
Oh yes, there is. The spring we're using is this magnetic spring. How far in you push the shaft or pull it out determines the stiffness itself. So it could go, I think, between positive and negative 100 Newton meters per radian.
So I mean, is there any remote control over that?
We didn't have it in our test. We will manually do it. But the idea is that if this were to be released in like real life, maybe you could have it change every few hours. Obviously, it requires some power. Actually, it requires quite a bit of force because of the magnetic resistance to change it. But every few hours will be realistic. Yeah.
Kind of responsive technology gonna change the whole problem, and we're gonna have a new optimization in terms of let's have a real-time data and response as soon as possible. We see some data.
Yeah. For our optimization, we kept just one value, but yeah, you could do it for each condition. Like have some discrete number of conditions, and then based on the condition, change that. Yeah.
Yeah, I think my question is going to be a little bit dry.
It's fine.
Because I study economics. Specific electricity markets, right? Because, I mean, when it comes to like generators connecting to the grid, they offer many services. And that's how they eventually make money. So I was wondering, like, there's a lot of conversation when it comes to renewables and grid following and grid forming inverters and whatnot. So, like, how do you think, like, wave managing converters can actually, like, add to that conversation of providing other services than just energy, but giving some stability to the grid as well?
Yeah, that's a good question. Grid stability is a big problem with renewables. That's another reason why a diverse renewable portfolio is beneficial. Because when the wind is not blowing, maybe the sunlight is, right? wave energy is way more stable. So it's way less variable. It changes over the seasons, but normally the day-to-day, hour-to-hour is pretty stable. So that makes it attractive. And I'm not sure I captured the whole of it, but you were asking about the economics of it as well. So one way it could be economic is, again, if you have a given target, like you want 90% renewable or 100% renewable, doing it with wind and solar alone would be extremely expensive because of the having to overbuild for the winter months when wind and solar are low. If you can put in waves, even though it's more expensive, significantly more expensive right now, it still might overall be cheaper because it reduces the amount of extra redundant wind and solar capacity you have to install. And then economic-wise, the other thing I'll mention is that we recognize that going from nothing to the grid is going to take a lot of time. So we're working in applications that are much smaller scale than the national grid, but that can be like a stepping stone into getting there. So we work with like military AUV applications or oceanographic buoys powering their sensors, or remote island microgrids. There's many remote communities in Alaska that pay like $12 to $20 a gallon for gas, and they have diesel generators for electricity, where this might be economical, so we've done studies like that. But right now, it's far from being economically competitive on its own at the grid level. But that's also where solar and wind were 15 years ago.
Perfect, last question.
Well, I'm curious to see like how average power, like output power changes, like for an optimum state. Let's assume, like with the variation in water density, if it's less, if there's like less salt in there, or there's like more salt, or with the temperature of the water as well. I'm not sure if that's considered.
So the change in density is significant for some applications. For wave energy, it's not. I mean, we're talking about 1,000 kilograms per meter cube to maybe 1,020 kilograms per meter cube. So it has little effect. There has been studies of wind wave energy converters in like the Great Lakes, which are freshwater. But I'd say it doesn't have much of an effect. But I will mention that there are other ocean technologies that are way behind in the research area. Not many people have looked into them, but the potential is huge, and that includes salinity gradient and thermal gradients, especially where rivers meet the ocean in a very short, like let's say 1 kilometer distance. You have huge changes in energy from temperature and salinity, and there are ways to extract energy from that. So actually, if I go to the beginning, this gray here is ocean thermal. So there's a big amount of energy in ocean thermal in the US, but there's no good technologies. There are some prototypes and stuff, but it's not as researched as current and wave. But there is a lot of resource, so there's a lot of opportunity there for that.
All right, thank you, Carlos.